So I think this topic requires its own video because it's a little weird as you get started. So let's talk about mole-mole ratios because this is really the heart and soul of stoichiometry. This concept is how we can relate chemicals with two different formulas in a balanced chemical equation and start with one thing and end up with something else, because really these are from the balanced chemical equation. That's like our chemical recipe. So as we're reading our chemical equation, remember that those coefficients, those are the moles. So let's get started with my most controversial example of this, which I'm not accepting like anything else about this, okay? So you're just going to have to deal with what I'm about to say, and that is one grilled cheese sandwich needs 2 pieces of bread, and that's not the controversial part, but it needs 3 pieces of cheese, okay? So I've got my 2 breads and my 3 cheese, and when I combine those, I get 1 grilled cheese sandwich, okay? And I'm not accepting other values of cheese for this. It has to be 3 pieces, okay? So that's just it. So if I wanted 2 grilled cheese sandwiches, if I wanted to double that, how many pieces of cheese would I need? Well, if I doubled this, so I multiplied that by 2, I could also double this by 2 because this is my recipe and that's what everything would be. So I would need 4 pieces of bread, I would need 6 pieces of cheese, and I would need 2 grilled, and that's how I would get 2 grilled cheeses. Similarly, I could what if I don't want 2 grilled cheeses? What if I wanted half a grilled cheese? So if I wanted to end up with 0.5 grilled cheese, I would have to have 1.5 cheeses because I'm dividing this by 2 each time, and I would need only 1 bread. All right, so I hope that you can see that that's the idea behind these mole-mole ratios, is really we're just taking our recipe and we're changing it by a certain amount, and when you change one component of this recipe, you change everything. Okay, and we can apply these same principles to regular old chemical equations as well. So if we have something like iron 3 oxide combining with 3 carbons to make 4 moles iron, and 3 moles of carbon dioxide. It's the same idea. And so we can do these ratios by whole numbers. We could also do ratios by fractions. And the whole thing is just figuring out that when you're changing one number, you have to change every single one of them. And that's where this idea of the mole-mole ratio comes in, because in any of these problems, you're going to only be asked about 2 compounds, and it doesn't matter if they're products or reactants or whatever, because these ratios are set in stone by the balanced chemical equation. So for example, let's just practice writing out some of these ratios. So if I wanted to write out, like in my original example, the ratio of bread to cheese, I had 2 pieces of bread for 3 pieces of cheese. I could just as exactly easily and exactly correctly say 2 moles of bread and 3 moles of cheese. So just keep that in mind. Every one of these coefficients, which I'm underlining right now, each one of those is just the moles, and that's where we're going to get the information for the mole-mole ratio. So we could say 2 moles of Fe2O3, iron 3 oxide. That's in ratio. So I'm going to write my equal sign with 3 moles of carbon. So if I was focused on figuring out how much carbon I needed to react with a certain number of moles of iron 3 oxide, that's the ratio I would use. And similarly, I could look at 3 moles of carbon. That would equal 4 moles of Fe. So whatever 2 compounds that you're looking at, so here's a reactant, here's a product, and here's the ratio for that. It doesn't matter which 2 compounds you're looking at when you're considering the balanced chemical equation, that's exactly what's going to give you your mole ratio. We just look at those coefficients right in front. Products, reactants, if they're both products, if they're both reactants, if one's a product, if one's a reactant, it doesn't matter. We're just looking at the coefficients, and that tells us the mole ratio. Okay, so maybe one more. Let's do both of the products. We would get 4 moles of Fe equals 3 moles of CO2. And what you really need to be able to take away from this is whatever the coefficient is, that's the moles, and we're using those exact numbers to write these mole ratios. And you can do this for this equation, for our grilled cheese equation, or for any equation that you come across. So your big takeaway is those mole ratios come directly from the balanced chemical equation. Those are the coefficients in front. Those tell us the moles. What you're going to do when you're given a problem is you're going to see those two formulas that you need, and those are the 2 moles that you're going to be comparing in the balanced chemical equation. So make sure that you're recognizing those ratios. Sometimes those are easier, like I want to double this recipe, and sometimes it's harder, like, oh, I only need 0.6 grilled cheese sandwiches, or only 0.6 moles of that. So take your time, do your best. Those mole ratios is what's going to convert from one chemical compound to another chemical formula. Best of luck. I hope this has been helpful.